last class we finished your synchronous machines, synchronous motors, right? And till now we discussed DC generator, DC motors, synchronous generators. So now what we studied is that all the machines we studied till now, rotating machines, they are all doubly fed machines, right? All like DC motor. DC motor is we are giving to supply to the armature as well as the field. And in the synchronous motor also same, right? They are doubly fed machines. So now in case of induction motor, it is singly fed. That means we'll give only one supply to the starter. There is no other supply. And therefore this kind of machine is most suitable for industrial application. There is no complexity. You might have found in your lab also, connecting an induction motor is the most simplest, easiest. Other machines it is little complex, but connecting the induction motor, simply you connect the auto transformer directly to the 3-phase, right? That is the most simplest connection you have seen. So we'll see here just a constructional feature, a small brief overview of the constructional feature of the induction motor. What you are seeing here, you have seen this in your lab also, the same machine, but I am showing little bit the inside structure. So this is a squirrel cage induction motor. Squirrel cage already we have seen in the synchronous motor. What do we mean by the squirrel cage? We have put the damper of squirrel cage in the synchronous motor in order to make it self-starting, right? So here we can see here the rotor structure. These are the conductors. We can see here, right? And these conductors are sorted at both the ends, and therefore it is known as the squirrel cage structure. And these pointed parts you are seeing here, they are the cooling fins. When the rotor rotates, it actually takes the air and it acts like absorbing the air, so that it acts like a coolant. The air acts like a coolant to the rotor circuit, right? And what we are seeing outside structure is, this is your base where the rotor actually sits on the platform, right? And there is a fan cover. The fan is here. This is your fan, right? The cooling fan, which actually exhausts the heat generated inside the machine to outside. Okay. And then your drive sealed both side. Okay, non-drive sealed and drive sealed. They are like the casing. And this is your shaft. Shaft is very essentially required in order to connect the load, external load to the shaft. Okay, and this is your external connection point where we give the supply, that is known as terminal box, right? And here we have eye bolt, that is eye bolt, that is a bolt where we can use it for lifting the motor and placing it somewhere, right? And these are the structure, external structure we can say. And on your starter we have the distributed 3-phase winding, as in case of synchronous motor we have seen. On the starter we have 3-phase distributed winding. Okay. Yes. Okay. So now we'll see little bit the distinction or the difference between DC or synchronous motor and induction motors. So as already I told, these motors, DC and synchronous motors, are doubly fed machines, and induction motor is singly fed machine, where we fed only one supply to the induction motor. And conduction, this is conduction type DC and synchronous motors, because we give the supply by connecting directly the supply to the rotor. But here it is induction type. Like you have studied your transformer. In transformer, this is the power is being transformed. There is the process is induction type, right? It is the principle of Faraday's induction, law of induction. So induction type. So here also the induction machine working principle is induction type. That means we give the supply to the rotor through the inductive principle, not conductively, okay? And then in the DC and synchronous motor, we require commutator or slip ring in order to supply the power to the rotor circuit, to the field circuit. But here in case of induction motor, we don't require anything. By that way, we actually reduce the losses and the brass and the slip ring. Okay. Then, because of this, more losses occur in case of DC and synchronous motors. In induction motor, we have less loss as compared to the motors, DC and synchronous motors. It is efficient, and induction motors are highly efficient. And for DC and synchronous motor, we need DC or both AC and DC. But in case of induction motor, we need only AC. Already we know this, right? For DC motor, we need only DC supply for both armature as well as the field. But here, in case of synchronous motor, we need AC and DC both, right? Okay. But in case of induction motor, we need only AC supply. So these are the major distinctions. So from this, we can see that the principle of, or the constructional feature and operational principle, they are much more easier. It is not so complex as compared to DC and synchronous motors. So therefore, in industry, most of the industrial drives, they adopt this induction motor. Even we have seen electric vehicles also nowadays, they are coming up with induction motors. Okay, so we'll see, already you have studied perhaps, and also I have given an introduction how a coil in the time varying magnetic field, it actually behaves, right? So when the starter winding of a polyphase induction motor is connected to polyphase supply, what will happen? It will produce a revolving magnetic field. At last class I was discussing how the revolving field is being generated, right? And the strength of the magnetic field remains constant. The field rotates at distance covered by two poles for each cycle of the input wave. How it is, we'll discuss. And the force acting on the conductors of the coil wound on the rotor causes the rotor to rotate. So it produces the force, and by which the rotor rotates, right? And the rotor turns at a speed lower than the speed of the revolving field. So the speed will be less. Like yesterday we were discussing, when we put the squirrel cage on the pole faces of the synchronous motor, it starts rotating, but it cannot achieve the synchronous speed, right? But as soon as it starts running, and the synchronous speed gradually it is connected to the grid, then it achieves the synchronous speed, or else we can, through the prime mover, we can take to the synchronous speed, right? So already we have discussed this. When we give this three-phase supply to the three-phase distributed winding, what will happen? Already we discussed in the last class. So these are the current waveforms, and at different instants we checked how the flux will behave, right? And then we have plotted the flux and the resultant flux here, right? And we saw that as the time passes at different instants, the resultant flux also moves in this direction, clockwise direction, right? So, but the magnitude of the resultant flux becomes 1.55 m, right? And similarly, at instant 2, when omega t equal to 60 degree, we have also seen that it rotates by 60 degree. Previously it was here, phi r1, now it is rotated in a clockwise direction to phi r2 position by an angle of 60 degree, right? The magnitude remains same. And similarly for instant omega t equal to 120, again it will rotate by another 60 degree, right? So what we observed is that if we have number of poles per phases is 2, that means your supply frequency if it is, let us say, f, your supply frequency is f, then the frequency of rotation of the flux, resultant flux, will also f. Okay, but when the number of poles increases, let us say the number of poles becomes 4, then your supply frequency is f, then your frequency of rotation will become 4 by 2 f, right? That is twice of f. So as the number of poles per phase increases, the rotation of the frequency of rotation of the flux, resultant flux, will increase as per the number of poles, right? That means the relation we can say is that Fs is equal to P by 2 F, right? Okay. So this is what here we have shown here, that your Ts, that means the time taken by the flux to rotate once, is equal to P by 2, the time period of the supply frequency. Okay, and from this we can find the speed of the rotation of the resultant flux, that will become 1 by Ts, so that is equal to twice of F by P, and this is in RPS, that is revolution per second. Now if we will convert to the RPM, then it will be 120 F by P. We have to divide it by 1 by 60, so it will become 120 F by P. Okay. Now your Ns will become, if you know the supply frequency and from the constructional features, if we know the number of poles per page in the induction machine, then we can find the speed or the synchronous speed at which the flux is rotating in the periphery of the armature surface is 120 F by P. And if we convert it to omega, so omega S will become equal to 4 phi F by P, it is equal to 2 by P omega. Okay, so this is your expression for synchronous speed. Okay, now this is what the picture is showing, your revolving field which is rotating at omega S. Now your rotor is not achieving the synchronous speed, so what will be the relative speed between the speed of the flux which is rotating in the air gap and the rotor? That is, I can write as NR. So NR will be equal to NS, that is the synchronous speed of the flux, minus NM. NM is the actual speed of the motor. Okay. So now if you write it in omega R is your angular speed of the rotor, and omega R will be equal to omega S minus omega M. That is relative speed of the rotor. So this is called slip speed. This relative speed is known as slip speed. Okay. So as we know the slip speed, we can find the slip, percentage slip of the rotor. So percentage slip I can write, it is omega R by omega S into 100. If I'll multiply with 100, it will become percentage, or it will give us in per unit. So your slip will be relative speed by synchronous speed. So relative speed is omega S minus omega M by omega S. So it will become so from that we can find omega M in terms of the synchronous speed, right? So that will become 1 minus S into omega S. So that means the actual speed, if the slip is given of a motor and you know the synchronous speed, you can find the actual speed of the motor, induction motor, right? And now if we'll find the frequency of the, because of the induction principle, there is an EMF in the rotor circuit, and what will be the frequency of the EMF in the rotor circuit? Okay, so that frequency I can find it from this expression, that is Fr will be equal to Pnr. Nr is the relative speed of the rotor with respect to the flux around in the air gap, right? So Fr will be equal to Pnr by 120. With this same formula, but just we are replacing N with Nr. Nr is your relative speed, right? So if I'll substitute instead of nr ns minus nm, so it will p into ns minus nm by 120. So then just little bit manipulation, I will find s into f. So that means your relative or your frequency of the EMF generated in the rotor circuit will be equal to s times the frequency of the supply we are giving to the starter circuit. Okay, this is the expression in order to find the frequency of the EMF in the rotor circuit, right? Okay, now this is a small problem. You can do it. Calculate the synchronous speed of a 4-pole 50 Hz 3-phase induction motor. What is the percent slip if the rotor rotates at a speed of 1200 rpm? Quickly, 1 minute. Okay, so if we'll find ns, it will 1500 rpm, then it will be 0.2. Okay. Now we'll see the revolving field with 2-phase winding. We saw for 3-phase winding. Now we'll see the 2-phase winding. So is there any motor having 2-phase winding? Have you seen 2-phase motor? In the lab you have seen 2-phase motor? Not seen. 1-phase, single-phase motor? You have seen in the lab? Here is a single-phase motor. This is an induction motor, single-phase. These fans are all single-phase induction motors, right? So at single-phase, this revolving field of 2-phase winding is essentially required for single-phase motors. Okay. Other principles will remain same because single-phase motor will produce a flux which is pulsating in nature around the surface, by which the rotor cannot self-start. The rotor cannot rotate. So therefore we need to split the single phase into 2-phase. So if we can split it somehow, then it will act as a 2-phase motor, and by that way it will have a net revolving field, net flux which is revolving at synchronous speed. Okay. So that because of that principle we need to know this revolving field of the 2-phase winding. Okay. In order to understand the principle of a single phase induction motor, we need to understand this 2-phase, because the single phase in case of single phase motor we use the capacitor with 2 windings are there in case of single phase winding. One is your auxiliary winding, one is your main winding. So both the winding they actually produce 2 fields, and because of that 2 fields we will have a resultant flux which is rotating at the synchronous speed. So this is the revolving field theory of 2-phase machine, right? So you can see here we have 2 windings, that is 2-phase winding. They are distributed around the periphery of the armature. One is H1, one is starting at H1 and it ends at F1, another one starts at S2 and ends at F2. Okay. And these are the 2 windings. So now we'll see the waveform of the currents. The I1 and I2, they will be apart 90 degrees from each other. Okay. And then if we'll see I1 and I2, the current, I1 will be Im sin omega t, I2 will be Im sin omega t minus 90 degree. 90 degree lagging behind I1, right? So it will become minus Im cos omega t. So then I will write the expression for phi. Then phi 1 will be phi m sin omega t and phi 2 will be minus phi m cos omega t, right? Now we need to find the resultant flux. So these are the 2 fluxes. Now how we will find the resultant flux? We can see here. So let us consider the instant where omega t equal to 0. So at the instance where omega t equal to 0, we can see the resultant flux here. At omega t equal to 0, phi 1 will become 0, right? And phi 2 will be phi m, that is the maximum flux, but in the opposite direction. Okay. So therefore The opposite direction means from 2 to 2 dash. This is phi m and this is your phi 2. And phi 1 is 0, so therefore your resultant flux is phi r is equal to phi 2. So that is nothing but equal to phi m, right? The resultant flux here phi m. And similarly at omega t equal to 45 degree, what will be the net flux? So your I1 will be here 0.707 Im, I2 is minus 0.707 Im, right? And then the net flux will be here, it is plotted here, you can see here. So one is phi 1 which is plotted from 1 dash to 1 and phi 2 is in opposite direction from 2 to 2 dash, okay? Now the resultant will be here. So if you will find the resultant of these two, that is phi 1 is 0.707 phi m and phi 2 is minus of 0.707 phi m, then your phi r is phi 1 square plus phi 2 square square root. If you will find it, it will give me how much? Phi m. So we can see the magnitude of the net flux or resultant flux is remaining same, that is phi m. But in case of 3 phase we found 1.5 phi m, right? But in case of 2 phase we found phi m. So what relationship you are finding here? If the number of phases is n, then your n by 2 phi m. Okay. So this is the relation we got. That means the magnitude of the resultant flux will be n by 2 phi m. Okay. And then at 90 degree also you will find the same. So no need to explain because you all understand. You can understand this. Okay. So now we will see, since the flux established by a single phase winding pulsates in time along with the same axis, it doesn't revolve. So in single phase motor, the flux doesn't actually rotate. It doesn't rotate because it pulsates in the single one time, the north pole, south pole, south pole, north pole, it will pulsate in one axis only, right? So therefore, in order to make it revolve, we need to split it. The windings are split to make it, one is auxiliary winding, other one is main winding, and then it acts as two-phase motor, right? So therefore the minimum number of phases must be at least be 2 in order to produce a revolving field of constant magnitude. At least 2 phase we need, therefore for single phase motor we need to split it, right? So these are some of the summary. The magnitude of the revolving field in a 2-phase motor is constant and is equal to phi m, where phi m is the maximum flux, and the magnitude of revolving field in the 3-phase machine is 1.5 phi m. So therefore for n-phase machine it will be 0.5 n into phi m. So the revolving field rotates at a synchronous speed determined by the frequency of the applied source and number of poles of the motor. Already we know the relation, right? And the rotor speed can never equal to the synchronous speed unless the rotor is being driven by the external prime mover. Like in case of synchronous motor, we use the external prime mover to catch the synchronous speed, right? Okay, here is a problem. Can you do it very quickly? 2 minutes. So now your NS is 1800, S is 0.025, FR is 1.5 Very simple, huh? So therefore solving the problem for induction motion in the induction motor is also easy, right? Huh? As compared to DC and synchronous motors. In all cases it is simple. Yeah. Okay, now we'll talk about the equivalent circuit. So already you know the equivalent circuit for most of the machines, that is under steady state condition. Like transformer you have studied, right? Equivalent circuit. Then we have studied the equivalent circuit for DC machines, DC generator, DC motors, then synchronous generator, synchronous motor. Now we'll talk about the equivalent circuit for induction motor. So because the principle is inductive here, so the equivalent circuit will be exactly equal to the transformer. Only little difference because it has a rotating part. So now what is the difference of in a transformer and induction motor? Can you tell? So a transformer is operating, the principle of induction same, induction motor is same, but the transformer is stationary. It is not rotating. Is it rotating, transformer? And the induction motor is rotating. Why the transformer is not rotating? Mechanical rotate. So why transformer we are giving 3-phase supply, right? Then why it is not rotating? Field current means we are giving 3-phase supply, there is a 3-phase winding, right? In transformer also there is a 3-phase winding. In induction motor also there is a 3-phase winding, right? Then why transformer is not rotating? It is very wonderful. The induction motor is rotating. Armature? But if we'll make it fix a bearing, will it rotate? Fix a bearing and make it cylindrical, will it rotate? इतना तक तो पढ़ लिया, आपको समझ में आ जाना चाहिए क्यों नहीं रोटेट। अरे इतना तक पढ़ लिए, ट्रांसफार्मर भी पढ़ लिए हम लोग, इंडक्शन मोटर आधा कर लिए। Why the transformer is not rotating? Who can say?
Because transformer है तो भोग नहीं होता, जिसके अंदर हमारी जो फ्लक्स लाइन्स होती है।
फ्लक्स तो होता है, ट्रांसफार्मर में फ्लक्स होता है, फ्लक्स लाइन्स होता है। They are also separated from each other. क्या नहीं होता? क्या? पावर? Huh? What is it? Energy conversion. Energy transform होता है ना? तो यहाँ पे कन्वर्सन इसीलिए हो रहा है, एक फ्री पार्ट है तो रोटेट कर रहा है। तो ट्रांसफार्मर आई विल मेक ए सेकेंडरी फ्री पार्ट, विल इट रोटेट? I will make the secondary as a free, like I will put the bearing shaft, will it rotate? This way means? This way, that way, nahi. The simple answer already we have studied, right? हाँ, रोटेटिंग फील्ड किस लिए होता है? वेरी गुड आंसर। रोटेटिंग फील्ड किस लिए होता है? हाँ, क्यों होता है? ट्रांसफार्मर में क्यों नहीं होता है? ट्रांसफार्मर में भी फील्ड होता है, राइट? व्हाई? नहीं, ऑलरेडी आई टोल्ड इन द बिगिनिंग। हाँ, इसमें रोटेटिंग फील्ड होता है, ट्रांसफार्मर में नहीं होता है। क्यों नहीं होता है ट्रांसफार्मर? नहीं, घुमा नहीं, आंसर नहीं है। यू आर एन इंजीनियर, यू हैव टू आंसर टेक्निकल। उसको घुमाना नहीं होता है तो उसमें नहीं। वो बोलेगा घुमा सकते हैं तो हम फ्री कर देते हैं एक पार्ट को, घूमेगा। विल इट रोटेट? Rotating, it is correct. He told that it because the revolving field, the rotating field is there in the induction motor. Rotating field is not there in case of transformer. Why it is not there? Because the transformer windings are not distributed. three phase. Like in the case of induction motor, the windings are distributed spatially by 120 degree, right? But in case of transformer, how the windings are placed? Huh? कैसे? What we call it? What is telling? Primary to secondary इसमें भी है. इंडक्शन मोटर में एक प्राइमरी एक सेकेंडरी है. You have not seen the picture of transformer windings, how it is placed? ट्रांसफॉर्मर तुम लोग देखे हो ना, लैब में तो है. How the windings are placed? एक साथ होता है ना. That is called concentrated winding. Okay. The windings are concentrated at one place. It is not distributed. Okay. Remember this. When the induction motors windings are not concentrated, they are distributed spatially by 120 degree. Okay. But in case of transformer, it is concentrated winding. For each phase, we have concentrated winding. For phase A, it is concentrated at one place. For phase B, concentrated at one place. For phase C, concentrated at one place. And over that, first we put low voltage winding, then over that we have high voltage winding, right? And then we take the supply. So this is they are concentrated winding. So therefore, it is not possible to generate any torque or anything in case of transformer. अगर डिस्ट्रीब्यूटेड वाइंडिंग होता ट्रांसफार्मर में, आप कोई बियरिंग फियरिंग नहीं लगाते तो क्या होता? ट्रांसफार्मर ऐसे ही घूमता ना, घूम घूम के टूट जाता. तो इसलिए दे आर कॉन्सेंट्रेटेड वाइंडिंग्स. ओके. बट द प्रिंसिपल ऑफ ऑपरेशन इज ऑलमोस्ट सेम, द इंडक्टिव प्रिंसिपल, राइट? व्हाट इज टेलिंग? लगा सकते मीन्स हाँ, यू कैन डिजाइन ए रोटेटिंग ट्रांसफार्मर. ओके. So this is the equivalent circuit. You have seen perhaps this kind of equivalent circuit previously in your transformers, right? So what these parameters indicate? Here is your supply voltage, right? Okay, this is V1, and what R1 indicates? R1 is the resistance of the primary winding. Here we call it resistance of the starter winding, right? And X1 is the reactance or leakage reactance. What is that? Leakage reactance or reactance? Leakage reactance. No reactance. Leakage, there are two. We saw one is leakage reactance, other one is magnetizing reactance, right? So what is the difference between leakage reactance and the magnetizing reactance? In transformer also you have studied, right? So what is the difference between leakage reactance and the magnetizing reactance? Leakage reactance is because of wires.
स्ट्रेट नहीं होती, वो ऐसे ब्लॉक में चली जाती है.
It is because of the leakage flux. Very simple. It is because of the leakage flux. Okay. The flux actually, when we see the transformer, let us say this is a core. This is one limb of the core, right? Let us say. This is the winding. And one flux is confined to the core, and some flux they actually pass through the core, but they will leak to the air or to the medium around surrounding the core. So this leakage flux actually, it is part of the main flux, but it is leaking to the surrounding environment. So this, because of this leakage flux, one reactance or one inductance comes into picture that we call the leakage inductance. And that leakage inductance constitutes this leakage reactance. Okay. And one is, we call it XM, which is your magnetizing flux, which is actually confined in the core. That is the magnetizing flux. So because of that magnetizing flux, which is actually confined to the core, and that actually links both the winding, primary and secondary. So that is because of that, what reactance is, it is called the mutual, or we can say magnetizing reactance. Okay. So this is in the transformer. Now similarly, we have also, in case of induction motor, we have one component of flux which is actually linking to both primary, or we can say the stator and the rotor both, and some flux which are linking to the air gap, they are not linking to the rotor. So that part will be this leakage reactance, and this is your magnetizing component, which is because of the magnetizing flux which is linking both stator and the rotor circuit, right? Now your rotor side, if we'll see, RR is your rotor resistance of the rotor circuit, rotor winding, and XR is your leakage. Then where is the leakage flux in the rotor side? How it comes into picture? Is there any flux induced in the rotor side? Yes or no? Yes? How the flux comes to the rotor side? How it is induced in the rotor side? In case of transformer, there is a secondary flux, right? In the flux generated by the secondary winding, is it or not? How it is produced? Mutual inductance, mutual flux, you can say, right? But that mutual flux is the cause of leakage flux. But how the leakage flux is produced? Because of the mutual flux, one EMF is induced in the secondary winding, right? And unless the secondary winding is connected with the load or sorted, unless there is a closed path of current, the secondary side flux cannot produce, right? So therefore, this reactance comes into picture when there is a short circuit or there is a load. But here in the rotor circuit is already sorted, right? Because I told in the squirrel case, the secondary side is sorted. So as it is sorted, the induced EMF generated in the rotor squirrel cage will produce some current in the squirrel cage bars, right? So because of that current, this flux is produced, and that flux will mutually link with the primary side, and some of the leakage flux will be there. That represents XR. So XR is your reactance because of the leakage flux due to the rotor current, okay? And RR is your resistance of the rotor circuit, okay? And E1 and ER, E1 is your primary side induced EMF, or we can say the stator side induced EMF, and ER is your rotor side induced EMF, right? And I phi, IC, IM, you know, IR is the rotor current, okay? So now we need to, so let us say the transformation ratio is N1 is to N2. Now I will transform the rotor side parameter to the stator side. So how I will do it? Okay, maybe tomorrow we'll discuss, not tomorrow, in the next class we'll discuss how further we'll see from the equivalent circuit how we can derive the expression of power, the power relationship, everything, okay? We'll see in the next class.